Now I think we're all ready to go with this morning's next talk by Dani Kaufman, who will be telling us about affine cluster.
Okay, yeah, so definitely thanks for the invitation to speak, and I think all the talks have been super interesting so far. So yeah, so I'm going to tell you a little bit more about cluster algebras, and I want to tell you about affine cluster algebras, which are in some sense the next stage beyond finite cluster algebras. So this is based on joint work with Zach Greenberg. And I include a lot of these pictures in my talks, so hopefully by the end you'll have some idea of what this picture is. I'll show it a bunch of times. So yes, I'm going to review cluster algebras a little bit. We'll talk about the finite cluster algebras, which have come up in a couple talks so far, and then we'll see what happens when we go to affine cluster algebras. And at the end, I'll hopefully tell you some relation to physics through this limiting cluster algebra, sort of similar to what Hugh was writing down at the end there. Okay, so we already saw a pretty good introduction to cluster algebra, so I'm just going to do it a little bit quick, but maybe nice to see the definitions again. So I always think about cluster algebras coming from quivers. So for me, a quiver is just this directed graph, and we just have this requirement that there are no self loops, or you can think of that as a one cycle or a two cycle. So there's a perfectly good example of a quiver. The way, just a comment that was before was, you can equivalently think of this type of quiver as a skew symmetric matrix. But I'm just always going to deal with quivers, so I'll draw pictures of the quivers. So how do we make the cluster algebra? We start by making a seed, which for me, I just think of putting some variables on the nodes of the quivers. So the seed is just really a pair of a quiver and a bunch of variables. And the cluster algebra, remember, is made by mutating the seed. So let's just review how we do that. So there's a perfectly good example of the seed. So how do we do this mutation operation? We pick our favorite node and variable that we wish to mutate at, and we do an operation that consists of two things. First, we mutate the quiver at that node, and then we exchange the variable at that node. So we get a new seed where all the variables are the same except for the one that we exchanged, and the quiver is the mutated quiver. So quiver mutation itself comes in two steps. We saw this before. For each pair of arrows sort of coming into and out of our quiver, we add an arrow sort of completing that cycle. And whenever we generate a two cycle by doing this, we delete it and delete the arrows in pairs. And then we flip all the arrows touching the node that we mutated at. So that's our little combinatorial rule for quiver mutation. Here's an example. In this example, we're going to mutate at the first node. So we have one arrow coming in and two arrows coming out. So we end up adding those two red nodes. That makes one two cycle. We cancel out. That leaves that one red node, one red arrow. And then we flip those arrows, and that's the mutated quiver. Something kind of funny to point out in this example is we actually really get the same quiver back again after switching nodes 1 and 2. That's definitely a coincidence. That's not usually going to happen when we do quiver mutation, but it happens in this example. Okay. The second part of this, the seed mutation, was replacing the variable. We get a new variable at the node we mutated at, and this new variable is related to the old variables by this exchange relation. So the new variable satisfies it's 1 over the old variable times this binomial, which is the product of all the variables coming in plus the product of all the variables going out. And then we call that the exchange relation. So the way we make the cluster algebra is we start with our favorite seed. We do all possible sequences of mutations, writing down all the new cluster variables we get, and look at the algebra generated by them. A nice way to sort of start to visualize what's going on with this is we can look at this just exchange pattern, just sort of organize all this into an exchange pattern. So these red circles represent our seeds. So for our initial seed is this one with x1, x2, x3. Then there's 3 different mutations we can do. We can mutate in x1, x2, or x3, and that gives us 3 new seeds, and we can keep going. And this mutation operation we mentioned before is an involution. So if I mutate back at x1, I end up back at the same seed. And a priori, we get this infinite tree of just doing all possible sequences of mutations. So this tree I call the exchange pattern. It's not unheard of to do some sequence of mutations and actually get back the original seed we started with. It turns out if we get back the original cluster variables we started with, we have to have also gotten back the original quiver. So we can take that tree and identify the spots that have the same seeds. And this graph will be called the exchange graph. And so that's the graph that is in some of the pictures I will show. So an important fact, due to Kaufman and Zelevinsky, this exchange graph really only depends on the mutation class of the quiver that we started with, right? So if we start with some seed, it depends on a quiver. If we do some mutations to that quiver and say, okay, we're going to start with that seed again, instead, we'll really get the same exchange graph. So if we're sort of interested in what this graph looks like, we really only care about the mutation class of the quiver. And so this mutation class is just the set of all quivers that are mutation equivalent to our initial quiver. So now I'm going to move on to finite cluster algebras. So any questions about my cluster algebras review? Okay. So the sort of general question maybe we're interested in is, what is the combinatorics of a cluster algebra? I give you some seed. You can ask, how many different clusters are there? How many different seeds do you find when you do the mutations? How many different cluster variables you can find? These are sort of maybe the most immediate questions. Is it finite? Is it infinite? So on. So the important fact here, proved by Kaufman and Zelevinsky, is the finite cluster algebras are exactly classified by ADE Dinkin diagrams. So a cluster algebra has finitely many clusters and seeds, cluster variables, so on, if and only if there is an orientation of an ADE Dinkin diagram in its mutation class. So here's an example. This Dinkin diagram there is A2. We pick some orientation of it in order to get a quiver. This quiver I call QA2, and we claim that this quiver, if we use that as our seed, we'll get finitely many clusters. So here's the example, the computation. This is a good exercise just to write down. We start with that simple seed. There's only 2 options for how we do the mutations, and we'll see that after 5 mutations, we actually get back the original 2 cluster variables. So the answer to our question is that there's 5 different clusters and there's 5 different cluster variables. This is pretty well understood example cluster algebra. So here's our list of ADE Dinkin diagrams. To get a finite cluster algebra, we have to have a quiver that is mutation equivalent to some orientation of these. It should be easy to convince yourself that it doesn't matter which orientation I take, they're all mutation equivalent to each other. ADE comes in 2 infinite families, these AN, DN diagrams, and then 3 special diagrams, E6, E7, and E8. And just to relate back to some examples coming from Grassmannians that we know, the Grassmannians G2N are type A, GR 3, 6, 3, 7, and 3, 8 are types D4, E6, and E8. This one guy, just to relate back to physics, is the same as GR 4, 7. So that one we've seen before. That's the E6 guy. So those are AD Dinkin diagrams. It's a pretty small list of cluster algebras that are going to be finite. If we choose anything else, well, it's not going to be finite. So the cluster combinatorics, right? This question of how many clusters there are, how many seeds, all this stuff really is controlled by the root system. So Hugh mentioned some stuff about almost positive roots and whatnot. So we can compute based on some data coming from the cluster algebra, or sorry, coming from the root system, we can compute the number of cluster variables with this sort of simple formula. It's equal to the number of positive roots plus n for those minus simple roots. If we know the exponents of the root system, we can compute the number of clusters with this sort of amazing formula, which I think is pretty surprising. And while I have some idea of why this formula is true, but I don't know if there's really a way that proves it in the sort of uniform way for each case. I think is sort of interesting, but I won't spend too much time on that. So really, the root system tells us everything about the cluster algebra in some sense. One nice fact I want to emphasize is that these Dinkin seeds, these are the seeds whose underlying quiver is an orientation of a Dinkin diagram. They actually tell us all the cluster variables. In other words, every cluster variable in the cluster algebra can be found in some seed that is an orientation of a Dinkin diagram. How do we do this? Well, there's sort of a convenient way actually to produce all the cluster variables. And this is following along this source and sink mutation path. This is actually the same as this tau operation that Hugh was talking about. But I'm going to think about it in terms of source sinks mutations. So sort of as an example, if I take D4, which was again type same type as GR36, I can start with why not start with a Dinkin seed, and I've picked an orientation where each node is either a source or a sink. Then doing one iteration of source sink mutation means I'm going to mutate at all the sources. That means mutate at x2, x3, x4, and then mutate at the sink, which is x1. So if I do that once, I get this new seed. I've done 4 mutations, this new seed with a bunch of new cluster variables. The claim is that if I just keep doing that, it has an order that's written in terms of the Coxeter number, and I'll find every cluster variable in the cluster algebra. So this is maybe a nice way. If I just want to know what the list of cluster variables is, I can just do this for a finite type cluster algebra. Okay. So here's just to show a picture of the exchange graph of this type D4 cluster algebra. This exchange graph shows, again, each node, each dot there represents a cluster, and the edges represent the mutations. The yellow vertices are all the Dinkin seeds. And specifically, this vertex here is the one that maybe corresponds to this this particular orientation of the Dinkin diagram. And then you can maybe convince yourself that my sources and sinks mutation path, which involves 4 mutations, sort of travels in a particular way, right? There's 3 different mutations I can do. I don't know if it's really showing up. There's 3 different mutations I can do for the 3 different outside nodes. And so really I do 3 mutations that moves me to this spot. It doesn't matter which order I did them in. So if I did 1, 2, 3, 4, 5, 6, so whatever, this is sort of a cube. And I'm traversing to the other side of the cube. That's the 3 mutations of the outside, and then 1 mutation along the middle brings me to here. So the action of traveling from this spot to this spot, this is 1 sources and sinks mutation path. And our little calculation says that the order of this thing is 4, and that just corresponds to traveling around the outside. Now you can notice that there are other clusters that are not Dynkin clusters, but our claim before was that all the cluster variables appear somewhere along this path. So certainly not every cluster appears along that path, but every cluster variable does. Does that make sense?
Sorry, what do you mean by Dynkin clusters?
Those are the ones whose quiver is an orientation of the Dynkin diagram. So sort of as an example, these green guys in the middle, their quiver is actually this oriented 4 cycle. And there's 6 of those in the middle. So those are not Dynkin seeds, but they're actually the ones that maybe come out of the Grassmanni in a more natural way. Okay. So just some more pictures, just to show 4 pictures. There's E6 and E8, which are types GR47 and GR38. We can just spit out this picture. And again, I think it's sort of interesting that in the picture, the Dynkin seeds are all of these yellow ones that are pushed around to the outside. And so maybe you can see that E6 has 7-fold symmetry, and that's having something to do with this being GR47. And again, GR38, all the Dynkin seeds are around the outside, and this thing actually has 16-fold symmetry, which is maybe twice this 8 here. Okay. Okay, so that's finite cluster algebras. Affine cluster algebras, well, I'll give you some definition of what an affine cluster algebra is, but really what it should be is the simplest cluster algebra that's not finite. One property that these things are going to have is that their quivers are going to be finite mutation type. That means the quiver itself is only mutation equivalent to finitely many other quivers, but the cluster algebra is still going to be infinite. So there's going to be infinitely many seeds and infinitely many cluster variables. So in other words, as you travel around, you see the same quivers over and over again, but you see them with new cluster variables. So before we do anything, let's just look at an example. I claim that this should be an affine cluster algebra. This is basically the simplest thing we could write down that is infinite. We just take this quiver with two nodes and 2 arrows, and we just start doing some mutations. And it's pretty easy to convince yourself that you're not coming back to x1 and x2 as you go down here, that the degrees on the top and the bottom are just going to keep getting bigger and bigger and bigger. Does that make sense? So this really is like the simplest cluster algebra that is not finite. So I claim that this is affine type A1. So the affine cluster algebras should be classified by affine Dynkin diagrams. What are affine Dynkin diagrams? So these are Dynkin diagrams that are obtained from the ADE Dynkin diagrams by adding one more node in a special place. And so I've shown you where the special place is for each class. One way I really like to think about the finite Dynkin diagrams is that they're exactly the graphs that don't contain any of these graphs. So back when I showed before, the regular AD Dynkin diagrams are exactly the graphs that don't contain a cycle, that's AN. They don't contain 2 trivalent vertices, that's DN, or a vertex of degree 4, that would be D4 affine, or a trivalent vertex with lengths determined by these. So at most, no length 3s from each, or no 2 things of length 4, or no thing of length 6. So to make a cluster algebra, I should take one of these affine Dynkin diagrams and pick an orientation of it and use that as my seed. One little note, slightly technical, but just to point out, in this AN case, it's a cycle. It sort of matters what orientation I pick. And it turns out the thing that matters is just the total number of arrows going one way and the total number of arrows going the other way. And so that really splits us into a family of cluster algebras, A, P, Q, where P are P arrows one way and Q are Q arrows the other way. But in all the other cases, we can just pick any orientation and it doesn't matter. Does that make sense? So this is cluster algebras whose quivers come from these orientation, from these Dinkin diagrams, are the things that I would call affine cluster algebras.
You want your P and Q to both be positive.
Yes, it turns out that, so yeah, P and Q should both be positive. It turns out if one of them is 0, if I pick all the orientations around the cycle the same way, that turns out to be mutation equivalent to a finite type D quiver. So really I want P and Q to both be bigger than 0. Integers bigger than 0. Okay, and that gives me the affine type A's. What do we want to say? Maybe I'll say that a little later. Okay, so here's an example. This picture I showed earlier, that was affine type D4. So in other words, I take my D4 affine Dinkin diagram, which looks like this. I pick some orientation of it and choose that as my initial seed, and then just ask what are all the different clusters I get. And so it spits out this picture. It's would be infinite, so I just cut off the computation at some point, and but you should get some idea of that, of what's going on. So it would just sort of repeat the same structure over and over again. And once again, these yellow vertices, those are all the Dinkin seeds. And in fact, the same argument or the same, if we're looking at the sources and sinks mutation path, this guy here would correspond to, for example, this node here, and then we can mutate at the 4 outside guys, which will travel me across this 4 cube, and then mutate at the middle guy. So if I do that, this composite is one sources and sinks mutation path. And if I keep doing that, I will travel along this sort of spine, and the cluster variables will keep growing. Now, one departure from our finite cluster algebras is that we actually won't find all of the cluster variables by doing this. So there's really something new going on. There's some cluster variables that won't be found here. And the most natural place to look for them is kind of as far away as possible. So there's something interesting going on at the bottom of this picture. There's sort of these seeds which seem to move very quickly along. And in fact, maybe you can convince yourself that whatever this mutation is, it moves twice as fast as this one. That this sort of moved me from this chunk to this chunk, but this guy actually moves all the way from this chunk to this chunk. So there's something going on at the bottom there. And this is going to be important for my story about affine cluster algebras. So it turns out there's a different type of quiver that lives at the bottom. I call these TPQR quivers. And I'll show a big table of them so you can get an idea of what a TPQR quiver is. But so this quiver here is what's underlying explicitly the seed at the bottom there. And this contains cluster variables that aren't found along the sources and sinks mutation path on the Dinkin quiver. So I'm going to tell you a little bit more about these things. So TPQR quivers, basically, what it is I sort of pick this this double arrow and I attach some oriented cycles to it, and then I make the tails length of P, Q, and R. So just as an example, this is a T3333332 quiver, and it has tails of length 3. That's a tail of length 3. It's a tail of length 3, and that's a tail of length 2. So hopefully it makes sense what TPQR is in general. I sort of have this middle part with this double arrow and oriented cycles, and then I can make the tails longer and longer and longer. So I claim that each of those affine Dinkin diagrams is mutation equivalent when I pick some orientation to a quiver that looks like this. And I didn't put any orientations on the tails because that part doesn't matter, but the orientation is fixed around where the double arrow is. And we can see that in our AN, right, there's really of this family PQ, it depends on where along the chain this double arrow gets placed, but in D and E6, E7, and E8, the double arrow has to be placed over the trivalent node. So these TPQR quivers should be thought of as another way of extending the finite Dinkin diagram to an affine Dinkin diagram, right? If I remove that blue node, what I'm left with is the corresponding finite Dinkin diagram.
Does it matter how you orient the edges on the line?
Yeah, so out here, this doesn't matter because I can switch the orientations just by doing some mutations sort of along the tail, right? If I picked an orientation this way, I can mutate here and flip it to that side. So all possible orientations on the tail away from this center core are possible and are mutation equivalent to each other. But this is really fixed this way with this oriented cycles. Okay. So these TPQR quivers are sort of just as important as the Dinkin quiver in the affine cluster algebra. So we should think the affine cluster algebra has two important parts. It has the part that was the affine Dinkin diagram and this TPQR part. So a fact I proved with Zach is that we can find all of the cluster variables sort of in a particular way. In the affine cluster algebra, they can either be found on a Dinkin seed, and I'll call cluster variables that are found on a Dinkin seed finite cluster algebra, finite cluster variables, or they can be found on the tail of a TPQR, and I'll call those affine cluster variables. So just to highlight what the tails are everything that doesn't touch the double arrow. So in this case, this is the tail, this is the tail, and this is the tail. So these are tails. So everybody that doesn't touch the double arrow, those are the tails, and those contain these affine cluster variables.
Does that mean you can reach all cluster variables by starting from two different seeds? One is the Dinkin.
Yes,
one is the TPQ.
yeah.
Only mutate on the.
Yes, sort of, not quite. You have to do a little bit of a special mutation sequence to find all of the affine cluster variables, right? If you just mutate along the tail, you'll sort of be stuck in one subalgebra. You can do we call it like a twist along the tail. And if you keep doing that on each tail, you'll find all of the affine cluster variables, but it requires mutating at the double arrow spot as well. I can explain.
Then what do you mean that they can all be done?
Every cluster variable is either in a seed that looks like a Dinkin diagram or in a seed that looks like a TPQR where it is on the tail. And there is an explicit mutation sequence that produces all of them. But it's a little bit more complicated than just doing mutations on the tails. Yes.
This is kind of Lauren's question, but can you get from any TPQR to any other TPQR along a sequence
Yes.
that stays only within TPQR?
No.
Okay.
Yeah, so that's, yeah, so you
Yeah.
can't, you have to just leave them for basically 1, 2, or 2 seeds, and then you'll get back Yeah, so there's a very short mutation sequence that connects all the TPQRs, but it just travels very slightly off TPQR.
Is it easy to see from the picture before?
Maybe,
I don't know. If you-
yeah, so there's a mutate, right, like, so only these things, sorry, only these guys are TPQRs. And you can maybe convince yourself that in order for me to get from this one to this one, I have to go up here and then back down. So that's the mutation sequence. And in fact, in this TPQR, no mutations here will, other than the mutation on the double edge. If I mutate at any of those tails, then I leave TPQR, it cancels out and I don't have the double edge. So, yeah. And I call these, I call these finite cluster variables because if I freeze them, I'm left over with a finite type cluster algebra. If I call the ones affine, because if I freeze them, I'm left over with an affine type cluster algebra of smaller rank. Okay. Another sort of fun fact is that there's a very convenient path that connects the Dinkin seed to the TPQR. And basically you just do the sources and sinks mutation path on a finite subalgebra and you go halfway around. So what do I mean by that? Here's an example. If I take my D4 on the left, there's the one that looks like the affine Dinkin diagram. I highlight out a finite type D4, keeping track of that blue node as the extending node. And then I do the sources and sinks mutation path on that finite type D4. And if you remember from D4, it had order 4, the sources and sinks mutation path. So I only do it twice. I go halfway around, and that lands me exactly at the TPQR quiver. And this blue node moves conveniently to the node that's sitting, the extending node on the double edge there. So that's a little bit kind of cute. They really are, in some sense, as far away from each other as possible in that way. Okay, so something I want to point out, these TPQRs, they have a sort of special mutation element, which I'm going to call gamma, which is basically just do a mutation at the blue node. And you should be able to convince yourself this is basically the calculation I showed in the example quiver at the beginning, that you actually get the same quiver back again, just switching the blue node with the black node underneath it. It just reverses, in this case, it reverses the orientations of all the arrows. So I call the element gamma, which is basically mutate back and forth on the double arrow, or equivalently mutate and then switch the two nodes. This is a particularly nice mutation element. So just to go back to our picture, this was our D4. These TPQRs lived at the bottom, and this mutation along gamma really moves us very quickly along this affine direction. Or moves us very quickly along this sort of infinite direction of the exchange graph, and really it corresponds to this A1 affine subalgebra that we showed this calculation before, where the cluster variables got very complicated. So sort of a natural idea, if we want to try to understand this, right, it really looks like there's some repeating piece of this graph, right, that each time I do gamma, I just move over to sort of a new complete chunk of the graph. And so the idea is, let's just try to quotient the graph by this mutation sequence. So what this means is just identify two clusters if they can be obtained by mutation, by sort of an application of this shift from each other. And I can maybe explain in more detail exactly what that means, but you should think of it as this mutation generating a shift, and I'm just going to quotient by that. I'm just going to identify the clusters that land on top of each other. And so we do get something that now has sort of finitely many clusters. And here's a picture of what it looks like in this D4 case. So this is just exactly this graph quotiented by this mutation. That make sense? Maybe, yeah.
Maybe you don't want to get into this, but you only define gamma when you have
Mhm.
TPQR. So how do you like extend
Ye-
that?
Yeah, so basically you can just for any other cluster, I can pick some path to a TPQR and then apply gamma and then do the path back. Really, this gamma extends to a cluster modular group element that acts on all the clusters. Yeah. But I want to define it using the TPQR. So this quotient actually generalizes some properties of the finite cluster algebra, sort of the exchange graph and the cluster complex of the finite cluster algebra. So here's some facts on this quotient. This sources and sinks mutation path is now finite order, and its order, all right, one is equal to 1 over chi. This chi is kind of like some Euler characteristic of some orbifold. That's why I called it that. But it's in terms of P, Q, and R has a simple formula. If we computed this out in this D4 case, we would get that 1 over chi was equal to 2. So the sources and sinks mutation path now has order 2, and we could maybe see that this mutation along gamma moved us looked like 2 chunks along. The number of cluster variables up to gamma is finite. We can write down a simple formula for it, and it splits into 2 parts. One that computes the number of finite cluster variables, which has a similar form where there's n plus 1. That's the rank of the affine cluster algebra. Cluster variables in each cluster, and then I do 1 over chi sources and sinks mutation paths, and that finds them all. And then there's a bunch of affine cluster variables that can be found on basically just by finding where all the TPQR quivers are. There's also, I really love this sort of amazing formula for the total number of clusters in the finite quotient. This sort of has a similar flavor to this formula involving the exponents of the root system. It's a simple formula in terms of P, Q, and R. Again, I can't prove this in every case uniformly, so you have to like check E6, E7, E8, but it has a uniform formula, and I think that's sort of great. So you kind of have to check case by case, but the formula is the same each time. So this finite quotient kind of looks like a this quotient kind of looks like a regular finite cluster algebra. Here's some more pictures of these just to show what's going on. They kind of in some way, again, these yellow nodes around the outside are the ones that look like Degen diagrams. These green ones, I think, are the TPQRs. The structure kind of looks the best on the outside and then turns into this fuzzy ball in the middle. I haven't really ever understood why these pictures look like this, but that's what they look like. In an example, in this E8 affine, this chi is 1 over 30. So this thing has 30-fold symmetry, and there's 226,000 clusters in there.
How do you make those pictures?
So it turns out there's a convenient way actually to compute when 2 clusters are differing by gamma. These pictures, I usually compute the C vectors of the clusters and use that to identify them. And it turns out if I use a sort of special framing that is obviously invariant under gamma, under this mutation by gamma, then it spits out all the different clusters up to this action sort of naturally. So this, in other words, this is sort of a natural thing to compute from these affine, from the perspective of these affine cluster algebras. Yeah.
What are the green things outside? I mean, at the bottom there. I remember the yellow one because I thought that the ones that
Yeah. So these these are all the Dinkin.
The green.
Yeah, yeah, and then in the
Sorry.
middle somewhere.
Just
are
because
the-
before they were yellow. so I'm
Yeah,
always
yeah,
like
yeah,
that, so.
yeah, sorry. Okay. So, okay, I want to give you some idea of what should the cluster algebra that lives on this like sort of quotient thing be. And I want to hopefully convince you that it has something to do with these square root guys that were appearing before. So any questions, any other questions about the affine things?
We could use Brian, only GR48 and 39 are affine, right?
So they are actually not affine, they're this double extended, I'll show that in a second. So, yeah, unfortunately, there's no Grassmannians that are actually affine, they skipped that. So, okay. I want to say that this is a little bit work in progress to understand exactly what's going on here, but there should be some limit cluster algebra that lives after applying gamma a ton of times. And somehow my infinite affine exchange complex should sort of turn into this quotient in this limit. So our sort of fact is that we can understand exactly what this gamma mutation sequence does. It doesn't change any of the affine cluster variables. Those are the ones that are living on the tails, but it changes all the finite cluster variables in a prescribed way. Really, it's just due to the sources and sinks mutation path a ton of times as well. But we can understand it explicitly by just sort of studying, in this case, what happens. So just to show sort of the solution of this problem, it turns out I can solve exactly what the cluster variables are after applying gamma. So gamma, remember, is just do mutations on the back and forth along the two nodes that are on the double arrow. And if I number my cluster variables starting with 0, x1, and then after I do gamma n times, I'll end up with the cluster variables xn plus 1. I can solve for an explicit formula for what xn is. And well, basically the formula satisfies some linear recurrence, and you solve just linear recurrence. And some of the coefficients that appear in here have the flavor of this square root, and they really are actually the A's and B's and stuff that show up in there. So this A guy here that appears under this square root is, I think, the same A that appears that Mark was talking about. I don't have a B here. The reason I don't have a B there is that I set all the frozen variables equal to 1. So if I remember correctly, the B there is only in terms of frozen variables. So it's a little bit lazy, and I just get rid of the frozen variables. So anyway, we can, if I define this lambda, which has a simple formula in terms of A, just lambda plus lambda inverse is equal to this A. And this omega guy, I can solve explicitly for the cluster variables and see that in the limit, they're really sort of just growing by multiplication by lambda. That's what I want to take away from this. So if I apply gamma a ton of times, basically this part should dominate this part. And in fact, whenever I evaluate my cluster variables at positive real numbers, this thing is always bigger than gamma, or gamma inverse is always bigger than 1. And so in that sense, this part really dominates. So when I do gamma a ton of times, what I end up with is basically lambda to the n times omega as the cluster variable there. Now, what's sort of interesting, if I assume that n is much bigger than 0, so that this term is way bigger than the z's, I can start to do some mutations, and I will actually continue to compute the correct cluster variables. Basically, so here's just an example. I have this cluster, and then I'm going to do some mutations. In this case, I mutated from here to here. I mutated Z1, Z2, and Z3, and there the there's a little typo. This should have a omega in it. There, the mutation rule is exactly the same. These are just exactly the cluster variable would get out. But something funny happens when I mutate at this bottom spot. So to go from this seed to here, I mutated at this bottom spot. And then in my binomial, one term has product of the outs, which will have a lambda to the 3n factor. And then the other term will be product of the ins, which will just have a lambda to the n. And so I am just assuming that lambda to the 3n is much bigger than lambda to the n. And so I just eliminate that part from the exchange. So in other words, so basically what I'm just left over with is that this variable is the product of these three divided by this one is equal to this guy here. Does that make sense? So in my exchange relation, one part had a much higher power of lambda than the other one, and I'm assuming that n is really big and lambda is big, so that I can just get rid of that part. So I can go around using that sort of mutation rule and compute what are all of the different cluster variables I get. And these cluster variables up to identifying these two as the same cluster variable, because they just differ by a single power of lambda, gives me all the cluster variables that should live on this quotient by gamma. And these cluster variables, if I pull out the finite piece, so for example, I computed out that lambda to the n and lambda to the n times lambda plus 1 omega over zi, those are cluster variables. If I pull out the part that just basically get rid of this lambda bit, if I pull out these things, which are finite, combinations that were given by this formula on the previous slide, I can recover the algebraic letters that are appearing in this G48 story. So these functions are exactly the algebraic letters that appear there. You can ask how many different ones am I going to get? Basically, doing a little calculation, it's easy to convince yourself that there's sort of P times Q times R different letters that are the ones that appear explicitly on the double arrow. There's more, there should be one for each of the finite cluster variables in general, but if I just compute the ones on the double arrow, there's at least P times Q times R. But there's a lot of multiplicative dependencies between these things. Like as we sort of saw, some exchange relations will just be a product of something divided by something else. So I can go through and calculate what all of these things are, but when I consider them up to how many are they as a multiplicatively independent basis, there's a lot less. So basically, I want to tell you in the last couple minutes, just this was a story, something about an affine cluster algebra having these sort of infinite cluster variables that should have something to do with the algebraic letters. Unfortunately, as was mentioned, G48 isn't actually an affine cluster algebra. It's rather double extended. So basically, if I start with my E7, Dickin diagram, which is in black, there were two different ways I could make it affine. I could either add the affine node in the red, or I could add the TPQR extending node in the blue. If I do both of those, it's double extended. So this this quiver here, this E7 double extended, is the mutation type of GR48. I forgot to put in the little orientations, but you have to pick the orientations of this part to be the oriented cycle. So really, this thing still has gamma, which is mutate back and forth along this double arrow. And I can compute sort of in that limit, just sort of assuming that it looks like a affine cluster algebra, I can compute that there should be P times Q times R different algebraic letters associated to that infinite limit. So that's 32 letters there. But it also really has another infinite direction, sort of obtained by freezing this node and viewing it as affine based on this red node. In fact, I can switch the roles of these two nodes by doing my sources and sinks mutation path on the E7 finite part that's underlying there. That exactly will move this node up here and this node down there. So really, there's another obvious affine direction that will give me 32 more algebraic letters. From each of those 32, it turns out there's only 9 that are algebraically independent, and so together that makes 18 that was mentioned before. Now, just to show a picture of what's going on here, this is the exchange graph for this E7 double extended guy, for the Grassmannian cluster algebra G48. And these sort of regions down here are the parts that contain the T BQR quiver, which was T244. And this limit down here really looks similar to the limit that was happening in our affine guy. And so this is gamma. And then somehow I can travel across to the other side. This was do half of the sources and sinks move for the E7 finite bit that switched the roles of these two extending nodes. And then I could do gamma tilde and compute another sort of infinite limit cluster algebra. The thing is that those two operations don't commute with each other. So in other words, if I go down gamma a little bit and then go across, I'll actually end up in a different infinite region. And these two operations sort of have a braid relation. And so this is where the braid group really appears, right? So there's also these other infinite regions, and there's infinitely many of them. And so it's a little bit strange that in this calculation from physics that we really only see algebraic letters from 2 different infinite rays. And so this is the same question of will algebraic letters from these other sections also start to appear in some limit. So I think that's pretty much everything I wanted to tell you.